Ever wonder how your phone's AI can analyze a photo and generate a description? Or how a robot might identify a cat in a satellite image, even if it's never seen one before? That's the power of vision language models, VLMs, AI systems that bridge the gap between visual data and natural language. But here's the challenge. Even the most advanced AIs struggle when confronted with entirely new data. Today, we're exploring how researchers are teaching these models to adapt, and why this breakthrough is reshaping the future of AI. Let's break it down. VLMs are trained on massive datasets of paired images and captions, learning to map visual patterns to linguistic concepts. Imagine teaching a child to associate a picture of a cat with the word cat, but on a scale that's astronomical. Models like BLIP use contrastive learning, a technique where the AI is shown thousands of image-text pairs, learning to group similar ones while pushing dissimilar ones apart. It's like training a robot to recognize a cat by exposing it to every possible variation, every fur pattern, posture, and lighting condition. But here's the catch. When these models encounter data outside their training, like medical scans, satellite imagery, or rare species, they falter. It's akin to asking a math prodigy to solve a physics problem without prior exposure. So how do we help them adapt? Researchers have developed 3 innovative strategies. First, prompt-based adaptation. Think of prompts as strategic inputs that guide the model's behavior without altering its core architecture. For example, adding a satellite image of a forest instead of just a forest directs the AI to focus on relevant features. It's like giving a traveler a map, helping them navigate unfamiliar terrain without rewriting their entire journey. Next, parameter-based fine-tuning. This approach adjusts the model's internal parameters to handle new tasks. However, it's a delicate balance. Over-modifying risks catastrophic forgetting, where the AI forgets previously learned knowledge. Techniques like robust fine-tuning use methods, such as elastic weight consolidation, or knowledge distillation to preserve core capabilities while sharpening new ones. Imagine refining a chef's recipe without ruining the original dish. Then there's feature-based adaptation, which refines how the model processes visual or textual information. By enhancing feature extraction, like sharpening image edges or clarifying semantic structures, the AI gains sharper perception. It's akin to giving the model better glasses or a more precise vocabulary. But the real game changer, the rise of multimodal large language models, MLLMs, like DeepSeek-VL and LLaVA. These systems merge text and vision into a unified framework, enabling tasks far beyond traditional VLMs. They're not just better at image captioning, they're redefining how AI tackles complex real-world problems. Take the XGen family, also known as BLIP-3. These models leverage high-quality data and advanced visual language adapters to excel at tasks like image description and question answering. It's like equipping AI with a more precise dictionary to translate between visuals and language. Then there's the LLaVA family, which transforms ordinary image-text pairs into instruction-following data. By fine-tuning a language model like Vicuna while keeping the vision encoder frozen, they've created a system that can follow commands, like describe this photo or compare these 2 images. The implications are profound. From medical diagnostics to autonomous systems, these adaptive models are pushing AI closer to human-like flexibility. As research progresses, the line between vision and language will blur further, unlocking new possibilities we've only just begun to imagine. Stay curious and keep exploring the frontier of AI.